So where we left off last week was beginning to talk about functors. And as you recall, the discussion we had was functors being basically having the function call operation defined in a struct or a class. Functors look like you're making a function call, but of course the power of them is under the hood. It's actually using a C++ method call or member function call. And that has a bunch of different benefits. And so what we're going to do right here is kind of talk about the benefits of functors, and then we're going to compare and contrast them to other things we've already talked about, like functions and algorithms and so on. So why would you use functors instead of using good old C++ functions or the C style functions? Well, one reason for that is that you want to use an existing functor that's already built into the C++ STL. And if you recall, at the end of last class, we talked about things like the arithmetic functors, plus, minus, and so on. We talked about the relational functors like less and equal to and so on. And then I mentioned briefly that there's these kind of logical operation functors like logical and logical or. I've never used those, but they do exist. Another reason for using functors as opposed to functions is because functors are easily inlineable because they're structs, they have methods, they can be inlined, and therefore when you use functors with your code instead of functions, the compiler can often do a better job of inlining. And then the third reason for using a functor as opposed to a function is that functors are objects, and so therefore you can have them store state if you need it. Now, you don't always need state, and in fact, there's situations where you don't want to use state, but when you do need state, functors can be a great way of being able to manage that state. So each functor does a specific operation. So one of the ways that they differ from functions and algorithms is algorithms typically do a bunch of things, or they carry out an algorithm, whereas a functor typically does one very focused thing. So it will do something like check if one value is less than another value, or check if two values are equal, and so on and so forth. Or check to see if a parameter is odd. Those are the kind of things you do with functors. So they're really more like piece parts of an algorithm. And in fact, as you'll see, as we've already talked about, we often use functors as predicates. So you can use them in an algorithm if you want to check a predicate as opposed to checking for a value. And of course, functors can have member variables, data members, which functions can't, obviously. And so as a consequence, there's certain things that you might want to store in a functor, like in the constructor of the functor, you might want to stash aside some initial value, or you might want to stash aside an O stream or an I stream or something like that, that can then be used in the context of the operation function call method. Okay, and then there's a bunch of different kinds of functors. There's comparison and predicate functors that return Boolean value. So things like is odd or is even and less, greater. Those are all examples of comparison and predicate functors. And then they're used to parameterize an algorithm, or they can even be used to parameterize containers in the case of the less functor, for instance. And then there's also a bunch of numeric functors. These are things that do arithmetic operations like divide, multiply, subtract, and so on. And normally they're used with numeric types like int and double and float, but in some cases you can also use these kinds of things with strings, so you could add things together. Okay, so that's just a quick overview of functors to provide you a bit more context. Let's go ahead now and talk about some more issues related to functors. So you can classify functors in various ways. For example, you can classify a functor based on how many parameters, how many template parameters they take. So there are, in fact, some functors, which we've looked at and we'll look at again later, that take no parameters whatsoever. Things like random number generators would be a good example. You just call the number generator and it gives you back the appropriate type of whatever you're parameterizing it with. So they don't take any arguments. The methods don't take any parameters, or the function call operator doesn't take any parameters. Another example would be the unary functor or unary function, which takes a single argument. So things like negate would be an example of that. And then the third category would be binary functions that take two arguments of whatever the types are that you parameterize it with and return a value, which is also something that you can control. So it might return a bool or an int or a double or whatever. You could also classify functors in terms of the Boolean results that they provide. So you can think about them in terms of predicates, which would be returning a single value, taking one argument, returning a single value, and then you can also have binary predicates, where you take two arguments and return a Boolean result. And we're going to look at a whole pile of different examples of that. And then there's also ways of classifying functors based on the types of operations that they support. If you recall, when we talked about container adapters, we talked about the priority queue. And the priority queue required a less than comparator. So you need to be able to have a functor passed in that supported the less than operation. And that's, of course, what less does, the less functor. You can also have assignable functors, so they could appear on the left-hand side of an assignment operator. All the functors that are in STL by default are assignable. And then you can also imagine having functors that allow for equality, so you can check to see if two things have the same value. Some functions require a less than operation, like sort, for example, or the set container. Other things require equal. And there's also a file called utility that defines other overloaded functions so that you can get the full suite of comparison operations in addition to less than and equal to. And then yet another way you can classify functors is whether they store state or not. And this is something that is actually pretty useful, and it's one of the things that clearly differentiates a functor from some other types of data and from functions in C++. So you can have stateless functors, which are pretty much like functions. They're pretty interchangeable with functions, in fact, the main difference being the inlining. You can have constant state, where you have a reference or a const that's initialized by the constructor but never changes. And then you can also have state that's mutable or variable. In that case, you could update it. For example, you might have a counter that gets modified every time the operation function call method is called, and so on. Here are a few things to think about. From an efficiency point of view, you can pass parameters to functors. Of course, you can pass them by value or by reference. If you're sticking to scalar types like int and double, if those are the types of things you're going to be passing in, for example, some kind of functor that checks if something's even or odd, you might want to just pass them by value. If you're planning on passing arbitrary types, which might be user-defined or might be classes that come out of STL, then you might want to consider passing them by reference or const reference. And of course, you have to be careful with aliasing, as you always do when you pass parameters, especially pointers. If you have lots and lots of small functors, you might end up with a lot of overhead, so make sure you use inlining properly. Also, it's almost always a good idea to define your functors on the stack instead of the heap, so don't allocate your functors using new, but instead just define them, and usually define them as anonymous objects that get passed as a parameter, one of the last parameters, to some kind of STL algorithm like countif or sort or findif and so on. And the other thing that you often can do is you can use lambda functions where appropriate, which is another way to strip down the overhead of defining functors. Functors are very powerful, they're very general, and they get used both by containers and by algorithms. Okay, so let us now turn our attention to actual code, and you get a chance to see how these things really work. And this will give us a chance not only to talk about functors, but also to talk about all kinds of interesting STL algorithms that use these functors in novel ways. Now, some of these things we will talk about in other contexts. We're going to talk about them later when we discuss algorithms, mutating algorithms, non-mutating algorithms, and so on. But for right now, I'm going to focus on the functor aspects. All the examples will demonstrate functors, but we'll also get a chance to kind of showcase some cool algorithms as we go along. So here are some of the different functors we're going to look at. These are the arithmetic ones, and as you can see, they're mostly binary. Negate is kind of the obvious exception here, but plus, minus, multiplies, divides, modulus, all those good things that you're familiar with if you've written kind of basic arithmetic code in C++. For each of the examples here, I'm going to show how to do this with functors, and then I'm also going to show how to do this with lambda expressions. And over time, as C++ has supported lambdas, they have become popular. We've talked before about when to use functors, when to use lambdas, but I'll kind of reiterate that in this discussion to keep it self-contained. You can see we're going to define a set here called a set, which is a set of floats. And by default, it's going to use the less than functor or the less functor to order the set in ascending order. And then we're also going to define B set, which is a set that's going to be sorted in descending order. So A set is ascending, B set is descending. I should probably call it D set for descending set. And you can see all I had to do there was just put in a greater functor, demonstrating how functors can be used both for containers, as we're doing here, and for algorithms, as we'll see in a moment. Now, once I've defined my sets, I go ahead and I pass these into these helper methods. And you can see these helper methods both take input iterators, beginning of the range and the end of the range. And let's just talk briefly about a couple things. People have asked some really good questions lately on the discussion forum, and I thought it might be worthwhile to kind of talk about some of those issues. So one question was, how do you work with an associative container like a set or a map when we know it's implemented under the hood as a red-black tree? How do we iterate through it linearly? And of course, the answer is very simple, and it's the same thing for all the STL containers. They have iterator methods, iterator factor methods like begin and end and cBegin and cEnd and so on. And all these factor methods are used to get you an iterator to the beginning and the end of the range you want to go through. And then up under the hood, there are operations like plus plus and minus minus and dereference and not equal and all those good things. And when you walk through any collection or any container, like a vector or a deck or a set or a map, the iterator is what dictates the order in which things occur. And of course, for things like vectors and decks, it's really easy. It's just sort of the order in which they're defined from 0 to n-1 or size -1. So that's pretty much a no-brainer. But with things like sets and maps, they're sorted, and they're stored in sorted order in a red-black tree. And of course, as you can discover if you play around with it for any length of time, the iterators return the ordering from beginning, which is, in the case of something like a set, the lowest element, to the final element, which is the largest element. And of course, if you use greater, then it'll go the other way around. It'll start with the first element in the iteration range being the biggest element, and then the last element in the iteration range being the smallest element. And that's just the way that iterators work. They go through every element, and in the case of the ordered associative containers like sets and maps, you get them in order. So it indicates it goes through the tree from smallest to biggest or biggest to smallest. In the case of unordered collections, it goes through in whatever order the iterator deems the most effective, but the order doesn't matter because they're unordered containers. So that was one of the good questions we had. And the best way to find out the answer to that stuff is just to sit down and try it out. So don't find yourself at a loss, confused. Just pick up your compiler and crank away and have a good time and see what it does. But if you think about it for any length of time, you'll realize why it's sorted them. It returns them in sorted order because that's the way that the iterators are defined for the ordered associative containers. So another question that we got asked was, why do we have all these different types of iterators in the first place? Why don't we just have one type? And the answer, of course, is not every container lends itself to every type of iterator. So for example, as we're looking at here, sets support bidirectional iterators. They go from beginning to end and end to the beginning, but they don't support random access because it's expensive to do random access in a set. You'd have to kind of search from the top. It would actually be pretty complicated. So as a consequence, we have sets and maps only required to support bidirectional iterators. So they omit all those funky pointer arithmetic operations. Conversely, with things like arrays, or rather vectors and arrays, but for vectors, for sure, they support random access. So that's a more powerful type of iterator category, and it supports a broader range of operations. If you think about the very humble forward list only has one pointer. So you can only go from beginning to end, not end to beginning. Well, in that case, we only need to support forward iterators. So the reason why there are these different iterator categories is because they're different kinds of containers with different characteristics and different kinds of algorithms that have certain expectations on the kinds of operations they need their iterators to support. And so by keeping things ordered in terms of input iterators and output iterators, it makes it possible to have more efficient implementations that do precisely what they can do and nothing more. So it also keeps the surface area of the abstraction as tight and cohesive as possible. So if you still have any questions about that, please don't hesitate to ask. But I think if you read the articles that I linked in Piazza, you'll find out more about the rationale behind why they have all these different categories, 5 of them, in fact. Okay, so as you can see here, we're going to call demonstrate lambdas, passing in the iterator to the beginning of the A set and one past the last element in A set. And then we'll show demonstrate lambdas as well as demonstrate functors. And we do this both for greater and less. So let's come down here and take a look at demonstrate functors. So this is going to show a whole bunch of functors, and it'll also give us a chance to reiterate some of the cool algorithms in STL. So you can see here, we're going to take an input iterator to the beginning and one past the end, the last. We define ourselves a vector because that's what we're going to store the items into. We print the contents from first to last, which of course will come out in sorted order, either ascending or descending, because that's what happens with a set with its iterators. And the first thing we're going to do here is we're going to apply the transform algorithm. Now, let's go see if we can find the transform algorithm. And let's see, hopefully it's here somewhere. So here's transform. You can see that it goes from the beginning of the iterator range to the end. And every time through, it takes the binary operation that's passed in as the 4th template parameter here, binary operation, which of course is a functor. And it says binary operation, apply yourself to the first element and the second element. We'll talk about what first and second are here in a second. And the binary operation applies itself to those parameters, takes the result, and then stores it into the output iterator. So you can see what it's doing is it's applying a binary operation to every pair of elements in a pair of ranges. And those pair of ranges you can see here are defined as being from first to last, that's the first range, and then from first second or first two to the implicit last two. So it goes through these 2 ranges and it expects the second range to be as big as, or at least as big as, the first range. And it applies the binary operation and then it stores the result into the binary, the output iterator. And then the first and second and result iterators are all incremented by 1. Okay, so that's pretty much what this is doing. And as you can see, what it's doing is it's going through this range from first to last, and then it's going through the range again. So it's going to go through the range and multiply every element in that range by itself. And then we take the results and we put them at the end of this initially empty vector called avec. And when we're done, we will have multiplied all the elements in the set by themselves and then stored them at the end of avec. So that's what the first operation does. And you can see here that we then print the results out. So we're basically doubling everything. The next thing we're going to do is we're going to use a different variant of transform. So this variant of transform is going to take 4 parameters instead of 5. And you can see here what it takes is an input iterator, an output iterator, and a so-called unary operation. And therefore, what it does is it goes through the range from first to last, and it applies the unary operation to every element in that range and stores the results into the output iterator. So whereas the previous version of transform, which fortunately is right down here, the previous version applied a binary operation to each pair of elements in 2 ranges, the unary transform applies a unary operation to each element in a single range. If you come back over here, what we're going to do here is we're going to use the DivideFunctor, and we'll go look at that functor in a second. And we're going to go ahead and bind it to be connected to the value 3 or 3.0. And then there's also a placeholder, which of course is going to be every element in the range from first to last. So what we're doing here is we're basically creating ourselves a new functor, anonymous functor called, it's basically a binder. We'll talk more about binders shortly. And it's going to divide every element in that range by 3. But the key thing I want to focus on here is divides. And where does it store the results? It stores the results at the beginning of the vector. So in this particular case, we inserted all the elements here, and now we are going to go ahead and divide everything by 3. And the reason that this, so anyway, so that's what we're going to be doing. We're going to be doing that particular element. Now, the reason why AVEC is big enough here, we don't have to do the back inserter thing again, is because it got large enough when we called the first transform. And now when we do the second transform, it's already got the elements in it, except we're just going to go ahead and overwrite them. So they're going to get overwritten at this point. For kicks, let's go ahead and take a look at multiply and divide. So here's multiplies. And what multiplies is going to do is it's going to go ahead and essentially apply this operation. And the operation that it's going to do is going to go ahead and essentially multiply. It's kind of hard to see here, but it's going to go ahead and multiply the 2 elements together. And same thing is going to hold true for divides. Divides, as you might imagine, is going to divide x by y, or the first parameter is divided by the second parameter. So these are just names for arithmetic operations. Now you might ask the question, why don't we just go ahead and use the arithmetic operations directly? And the answer is, that's a good insight, and we're going to show that in our next part of the example. But back in earlier C++, they didn't support the next part of the example, which is lambda functions. So the way to do this was by using functors and other things like binders and negators and so on. Now, even today, when we do have lambdas, it's sometimes useful to use the functors, the name functors, because it may be more obvious what's going on. You can tell at a glance what's happening, whereas with the functors, as we'll see in a second, sorry, the lambdas, you have to kind of look at the code a little bit more carefully. Okay, so that's the demonstrate functors example. Now let's go ahead and down and look at the demonstrate lambdas example. And here we're going to have the range from first to last again. And instead of using, it's the same algorithms. We're using transform, the 5-parameter version, which uses binary operation, binary functor. And then we have the 4-parameter version of transform that uses a unary functor. And in this case, the only difference is rather than having a functor defined as one of the predefined functors like multiplies or divides, we're just going to go ahead and use a generic lambda. Or in this case, it's a type-specific lambda. I could make it a generic lambda if I wanted to. All I have to do is just say auto. And that's probably not a bad idea, because then I can change my types here, and I don't have to recompile. I don't have to revise my code. I can just let the compiler deduce the types. So here's the same behavior, except this time, instead of using a functor, one of the built-in functors, we're going to write a little code that's going to do what that functor did, which was multiply its parameters, a times b, and return a result. So you can see here, this is the syntax for the generic lambda expression. And the same thing holds down here. In this case, instead of using a binder and divides and all this kind of syntactic stuff, we're going to go ahead and use a lambda function. And you can see it's just going to take the parameter, and the parameter here always corresponds to what's in that range, and it's going to divide it by 3. So let's run the code, and then we'll take a step back and kind of evaluate the pros and cons of different things. So you can see we come in here, and we start out with these values, and those get stored in a set, which of course means they're ordered. So when we come in the first time in here, we are going to write the contents out in order, and then you can see we come in here, and in the next thing we do is we go ahead and we'll multiply everything by itself. We print those things out, and then we go ahead and divide everything by 3, and we print those things out. And you can see how we do that both for the lambdas version and also for the other stuff. So anyway, just kind of illustrating how all these different things work. Now, the interesting thing to note here is that in this code, or why would you choose to use the lambda version versus the functor version? Well, I think it's maybe the case, arguably, reasonable people could argue this. This code, when you look at it, that's pretty darn concise. It's pretty clear that we're going to multiply those things together. You don't have to think a whole lot about that. This code down here, it's also kind of clear what's going on, but you actually have to write more code. Writing that generic lambda function actually takes longer than doing this because there's just a functor out of the box that multiplies. You look at the code, you know very quickly what's going on. In contrast, this version down here that's going to divide every element by 3, that's pretty clear what's going on, I think. In contrast, you come up here and you look at this crazy newfangled bind mechanism. That's actually more complicated, and I think it's a little harder to read. It definitely takes longer to write. So we're dividing a placeholder for the first element by 3, and we're binding, and I think that's more confusing than writing this code. So the point of all this is that you have to think carefully about how this is going to work for you, and then make a decision about what's best for your needs and your application. So we're now going to turn our attention to the relational operations. And these are the ones that you also are probably familiar with because we've looked at some of them before. Things like less and greater and equal to, not equal to, greater equal, less equal, and so on and so forth. And these can be used also with various types of adapters. We'll talk more about them, like binders and negators and so on and so forth. All right, so this time we're going to have 2 examples we're going to focus on. One, we're going to demonstrate the use of these operations on a string, and then we're also going to demonstrate these examples on an array. And I think we're actually going to use the bind functors here because bind second has been removed in later versions of C++. And bind has replaced it. Whether that was an improvement or not remains to be seen. I'm actually a little bit disappointed in bind. I think it's more complicated than it needs to be, but that's okay. You can always use generic lambda functions if you don't like bind. So let's take a look at the example. The first example here, we're going to make a string that says spaces in text, and there's a space between spaces and between in and text. And then what we're going to print the string out. The next thing we're going to do is we're going to use bind to create a binder that will bind the equal to functor. And let's go ahead and take a quick look at equal to. Equal to, as you might imagine, will do the equals operation or the equality operation. So that's pretty obvious. And we're going to bind whatever's in the spaces in text string, whatever the characters are, to the blank, so the space character. And so what this is doing is this is going through the range of that string from beginning to end, looking for every place that has a space in it. And as the function says, it's going to remove that. So this just tells us all kinds of interesting things, right? So we'll look at remove if in a second. But first of all, notice we're going through the range of the string from beginning to end. And we're going to basically look for everything that's a space, and that's what's called a predicate. So what's returned from bind here is a functor, an anonymous functor that will return true if the character at issue is a space. And then we're going to go ahead and remove it. So let's see how this is going to work. So what we're going to do first is we're going to call the find if method. And if you recall, what find if does is it takes the predicate and it goes from beginning to end in this range, and it tries to find the first character or the first element that matches that particular predicate. Now, if we end up with first equaling last, we know it didn't find it at all. So let's assume for sake of argument we find the first space, for example. So first will not equal to last. And then what we do is we go ahead and we walk through the remainder of the range, and what we're doing is every time the predicate doesn't match, in other words, every time we are looking up the character that we're trying to match against and we don't find it, then we're going to go ahead and move the contents of the iterator into, or write it over the first iterator. So we have sort of a temp iterator called __i, and every time we don't get a match, we're going to go ahead and copy into the first iterator the element that didn't match, and then we increment that first iterator by 1. So what's going to happen here is whenever there is a match, we're just going to skip over and ignore that character altogether. So it's just going to be ignored. It's not going to be copied back into the the range using the assignment of moving star underscore underscore I to star underscore underscore first. So we're just going to skip over everything that matches. And the consequence of that is we'll end up with a new range, or actually an updated range, where everything that matched has been removed by simply having something else copied over top of it. And of course, under the hood, that all works magically with destructors and all this other good stuff to clean things up. Now, what happens here is remove if actually has no earthly idea that it's working on a container. It doesn't know it's working on a vector or a set or a map or whatever. And in fact, to prove that, the next example we'll look at is going to use a different type. It's going to use an array, so there's no container in that case. It's just a good old native array. So how do we deal with this? Well, what happens here is we have remove if give us back an iterator to the new end. And that's the new end after we've copied over all the other elements and removed them. So to prove what happens here, we're then going to go ahead and print out the old string from beginning to end, ignoring the new end. And that'll show that there's still some characters left over at the end that haven't been erased. If we really want to get rid of those characters and update the container as opposed to update the container's contents, or another way of looking at that is we want to update the size of the container, then we go ahead and say erase from the new end, which is the iterator that was returned by remove if, all the way up to, but not including, of course, the end of the original string. And that will then readjust the string's length to erase those characters and make sure that they are also removed. And then we print out the new string. So that's what the algorithm does on a string. Now let's go ahead and look at exactly the same algorithm, except this time we're going to do it on an array. So in this case, we're going to have an array of characters, which says spaces and text, just like we did up here, except this is a string. And then if you look at the code, we're going to call remove if again, except this time we're going to say begin s, end s. And begin and end are convenience methods that work well on, or they're intended to work both on containers. So just for kicks, I'll update my container up here to do the same syntax. It works for containers like a string, as well as for an array. And so that's what's cool about begin and end. You don't really have to know or care whether you're dealing with an array or you're dealing with a container. It works the same way. And once again, we use our bind mechanism to bind equal to the space character. And this code will work identically to the code up here in terms of its behavior. But it returns a new end that corresponds to the new end. So now we've gone ahead and updated the end. And then when we print the S here, that will actually remove the characters because it will have overwritten the last character with the null. And so as a result, the string will be terminated, or the character array will be terminated at the right place with the null character. So let's go ahead and run this code and see what it does. And as you can see, it does what we'd hope it does. It starts out with spaces in text, where there's a space in the string spaces in text, or the array spaces in text. It then goes ahead and removes the spaces, but you'll notice that when we print this out, it still has some characters at the end here, X and T. And then after we do the erase, then spaces in text is what we'd expect. The string now knows it's done at that point. That updates the length metadata. And then down here with the array version, we do the same thing, except we don't actually have to do any erase. In fact, we can't do an erase because it's a built-in array and not a container. But we get the same effect. Now, we could also have rewritten this code here to get rid of the binder and just used a lambda function. So this is the same code as you see up here, except we have a lambda function being used instead of using a binder and equal to. And I don't know about you, but I actually kind of prefer the lambda function version. It's a little bit more clear what's going on, but your mileage may vary. Reasonable people could agree to disagree about which is the appropriate way to go here.